Hello, everybody. I do the first day of our school. I also say hello to Jens Groth for accepting our invitation and giving this talk in our school. Let me give you a short introduction about Professor Groth. Jens Groth has received his PhD from Aarhus University, and then he went on to be a professor at UCL, University College London. And he's currently the director of research in formal security at DFINITY, which is a well-known company in Switzerland, which is active in the area of internet, computer, and blockchain. Jens has made several important contributions in the field of cryptology. His interests include electronic voting, mixednets, digital signatures, public encryption, zero-knowledge proofs, and blockchain. Jens' research has received a lot of attention from the community because of its importance and significance in the development of zero-knowledge proof and digital signatures and blockchains. In particular, for non-interactive zero-knowledge proofs has been deployed in several practical blockchain and coins. His work, fortunately, has also been recognized. He has been awarded the Asia Crypto 2020 Test of Time Award, and he has also won the UCLA Chancellor Award for Postdoctoral Research. Today, he will be talking about zero knowledge proofs, the foundations of zero knowledge proofs, and non-interactive zero knowledge arguments. So, welcome, Jens, and we are very happy to hear your presentation. The stage is yours.
Thank you, Shahram. I'm very happy to be here. Okay, let me share my slides, and hopefully you can see this. Okay, so can you all hear me well?
Yes, we can.
Okay. Excellent. Okay, yeah. Right. So just so I'm going to talk about zero knowledge proofs, which is an area I worked on in several decades by now. I did copy some slides from old days at UCL, so that's why the slides say UCL, but I am a full-time employee at DFINITY now, where I'm the a principal researcher. So just a few words. DFINITY is launched the Internet Computer as a contributor to the Internet Computer blockchain. And it's a very powerful world computer running very fast. And it also has on-chain web, so you can use a browser. You could just go there and you can look at the dApps that are running on the Internet Computer. So we're very excited about that. But let me transition to the main topic today, which is zero knowledge proofs. So in this introduction, I want to cover essentially 4 areas. First, I want to justify zero knowledge proofs, though you've already seen some justification of that. And then I want to give you some definitions, talk about what kind of setup we need for zero knowledge proofs, what kind of statements we can prove, and the security about zero knowledge proofs. And then I want to give an introduction to a very common type of zero knowledge proofs called Sigma protocols, and also show how one can use what is called the Fiat-Shamir heuristic to make these non-interactive. And then the last part will sort of be devoted to efficiency. I want to take us from some simple Sigma protocols and go all the way to, where you have like really compact proofs with very little communication and very efficient to verify. And that's all like the state of the art of the exciting world today in zero knowledge proofs, which is like a super active area where people are doing lots of exciting work. Okay, so zero knowledge proofs tackle at its core a fundamental contest between privacy and verifiability. And quite a few years ago, there was a hedge fund led by a guy called Bernie Madoff. Laws, right? So I think that's the biggest scam in the history of the world. But more recently, we've seen speculation about exchanges in the blockchain space, right? And particularly, we saw the collapse of the FTX exchange, which also took quite a few billions of dollars from the users of that exchange. So there's this fundamental question, somebody's been entrusted with some money, right? And you may want to know whether they're still solvent or your money is gone. So we could imagine an investor comes, asks this very reasonable question, is my money still there, right? But we can also imagine that whoever is holding that money actually doesn't want to say so much about the money, right? So if you think about a hedge fund, then it has all these clever proprietary trading schemes, and it doesn't want to disclose that. So it cannot just disclose the portfolio, right? Because that would also tell something about what kind of activities it has and what kind of things it's investing in. So you have this situation where the investor wants to know some information, and the hedge fund is in principle not against giving that information to the investor, but it doesn't want to give more information to the investor. And as you probably guessed, zero knowledge proofs is a possible solution to this problem, right? So the hedge fund will act as a prover and the investor will act as a verifier. And the statement will be, yes, your money is still here. The hedge fund has a witness to this fact because it knows what the portfolio is. And it can now engage in a zero knowledge. At the end of the day, the verifier is happy and says, oh, okay, that's great. It's good to know my money is still there. And the two core properties we want from a zero knowledge proof system is that it should be sound, right? So that protects the verifier, that you can only convince the verifier if the statement really is true. And then the prover wants confidentiality of data, and that's the zero knowledge property. Okay, so what it guarantees is that you do convince the verifier, but you do not reveal anything else except the fact that the statement is true. So zero knowledge proof was invented in the 80s by Goldwasser, Micali, and Rakov, and they identified these two properties of soundness and zero knowledge, and also noted that it has to be complete, right? So you have three properties. So completeness says that a prover can convince the verifier when the statement is true. And soundness says that you cannot convince the verifier if the statement is false, and then zero knowledge says that you are not leaking information. And a couple of interesting things about how this came up. So my understanding is that they were really thinking about, what is a proof, and think of mathematical proof, but now from a computer science standpoint. And one thing they noted was that, that it can be zero knowledge, right? So if you think of what is a good mathematical proof, it's one that really explains why the theorem you're proving is true. And this is quite the converse, right? With a zero knowledge proof, you can convince somebody that a theorem is true, and you can tell them nothing about why it's true. So the other thing that was interesting was that their schemes to start out with were actually interactive, right? So it's a proof where you have a prover and a verifier, and you exchanges messages. And as far as I understand, mathematicians were objecting to that and saying, no, a proof has to be something you can write down, right? They are used to mathematical proofs. So they were also sort of like rethinking the process of how do you prove something. And maybe it was a little more like, a court of law where you have an accuser and a defendant, and you're sort of like talking back and forth and issuing challenges to each other. Okay, so let's get started with some applications. So I already showed the example of solvency, which is one application of zero-knowledge proofs. The way I got into it was that I was doing a PhD on internet voting. And in these protocols, the voters, they encrypt their votes to keep it private and send them to the election authorities. And then the election authorities can use multi-party computation to tally the votes without decrypting individual votes and see what individual voters voted. Now, the problem in these protocols is that, you could actually encrypt, because it's confidential, what's inside or secret, what's inside the ciphertext, right? So you can actually do the equivalent of encrypting negative votes, for instance, right? So that's like, reaching into the ballot box and taking out some votes. Okay, so the election authorities may, of course, be quite skeptical about the ciphertext that come in, and proofs can be used in this context, right, to prevent cheating. So the voter can give a zero-knowledge proof that the encrypted vote is indeed valid, but without revealing what the vote is, right? Now, the election authorities, they're protected by soundness, so they're happy. Now they know the vote inside the ciphertext is valid, and it's not going to mess up the election. And the voter is happy because it's zero knowledge, so the vote is still secret, it's still encrypted, and there's no information about what his vote was. Okay, so and back in the day when I was a PhD student, this was something that you could run on a computer, but if there were many candidates in a big election, it would take several minutes to create this zero knowledge proof. And I did a lot of work on trying to optimize that and got it down to a few seconds, right? And that's a theme that is also at play today, but a much larger scale. That now we've really pushed the efficiency barrier, and we have like very efficient zero knowledge proofs, and people are working very hard to make them even more efficient. And if we have like super efficient zero knowledge proofs, then it suddenly, it becomes a trust assurance you can use in many contexts, and it comes almost for free, right? So that, I think that would be really great. Okay, so the more general picture here is that in general, well, what goes wrong, right, if somebody's attacking a protocol? And quite often it's active attacks where somebody's signals, right? This is called an active attack. And zero knowledge proofs can be used to prevent active attacks, right? Because you can prove to the rest of the protocol participants that, you have actually followed the protocol. And because of the zero knowledge property, you're not revealing any confidential data when you're giving that proof. You're only saying, I'm following the protocol, but you're not revealing anything else. So that's sort of like why zero knowledge proofs, conceptually speaking, are super powerful and very useful. Okay, and they're used in many applications. So voting was one, but you can have auction protocols where you want to prove that, it was really the right bidder who won the auction, but still keeping the bits private. You can use them in eCash, in digital signatures, encryption, multi-party computation protocols, and cloud computing to prove that, whatever the cloud produces to you is actually correct. Okay, and for all of them, the theme is that when we use zero-knowledge proofs, we prevent deviation from the protocol and give security against active attacks, right? And if we can rule out that participants are deviating from a protocol, we actually get a much easier design question. We can reduce the design question of some security conscious protocol on the internet or elsewhere to just consider, let's build a protocol that's secure against participants who actually do follow the protocol. So also from a design perspective, it's very nice to have zero-knowledge proofs in the toolbox. Okay, so I want to talk a little about how powerful zero-knowledge proofs are and the kind of statements you can prove, right? So there's some statement that the prover claims to be true, right? And to give a bit of context, so I don't know if everybody has heard about P and NP, but I thought just to be on the safe side, I'll give a brief introduction of officially decided. So what that means is that if a language is in P, then there's a polynomial time decision procedure to tell for an instance whether that instance is in the language or is it not in the language, right? So an example could be that maybe I give you 3 integers, n, p, and q, and I claim that n is the product of p and q, right? And it's pretty easy for you to check. You plug those numbers into your computer and do the computation, and it will tell you whether I'm honest or not. Or maybe I'll give you a program and say, here's an input and this is the output I got. And, again, you can just take the input, run the protocol, and I'll check that the output matches. And actually that's quite often what happens in the blockchain space, that you do this replicated computation to ensure that even if there's a single point of failure, you can still continue and you still have with the computation. Languages in NP, so this is a bigger class of languages, and those are languages that can be decided efficiently if you have a piece of advice, which is called a witness. Okay, so a language is in NP if there's a polynomial time decidable relation of instances and witnesses. Okay, and an instance is in the language if and only if there's a witness that matching witness such that this pair belongs to the relation. Okay, so here, and note that the instance may not be efficiently decided if you don't have the witness, right? So NP could be larger than P. Okay, so an example again, if we take, let's say we have an integer, right? And then I could claim about this integer that there are primes p and q such that the product of p and q is n.
Excuse me, Jens. I mean, do you changing the slides because it doesn't change this? I mean, we still are in slide 10. I was surprised a little bit.
Oh, okay. Yeah, that is surprising.
Yeah, because we saw we saw this slide once, but then disappeared and just we saw the slide 10. Sorry, I thought maybe.
I have been changing slides all the way. Oh. So that is unfortunate. And I don't know why it would jump to...
Maybe you can try again. We can see, I guess it should work. It was working, I mean, smoothly, but then in this one...
So was it slide 10?
No. Just no. We saw, I mean, it till slide 10, but after 10, it didn't change.
I see. Yeah. Okay. So this is slide 10. And this is slide 11. Okay, sorry. Okay, so let me just recap here what I was saying, okay? So P stands for polynomial time, okay? And languages in P are sets of instances where you can decide in polynomial time whether that instance belongs to the language or it does not belong to the language. So as an example, you could have 3 integers n, p, and q, and they would be in the language, an instance in the language, if n is the product of p and q, right? And it's pretty easy to check this. You just plug in the numbers and check whether n is the product of p and q. We have efficient multiplication procedures. So that is an example of a language in P. And in the blockchain space, such as the internet computer, we also do replicated computation, right? So if you have a program, you have some input, you get some output, right? Anybody can replicate that. If they have both the program and the input, then they can just run the same computation and check whether they get that output. So that would also be an example of a statement which is in P. Okay, NP are languages that can be efficiently decided if you have some advice, you have some witness to the statement. Okay, and languages in P are defined by polynomial time decidable relations. Okay, so a statement is in this language, NP language, if and only if there's a witness such that the pair is in the relation. Okay, and here you need both the instance and the witness to efficiently check that it's in the relation. So an example of that could be the statement that here's an integer n, and n is a product of 2 primes p and q, right? And the witness would be p and q, and if you have the witness, then you can take p and multiply it with q and check that it gives you n. Okay, so with a witness, that is an efficiently decidable instance. And if you have a program and an output, you may claim that this is the output of some legitimate input. And then the witness could be that input, right? Now, if you know the input, if you have the witness, then it's easy to check that you can run that program on some input and get the output. But if you don't know the input, then it might actually be very hard to check, even if it's a fast and efficiently computable program. Okay, so it's pretty clear that if a language is in P, then it's also an NP, right? Because if you can decide it efficiently without advice, without a witness, then you could just use the empty string as the witness. Now, it's believed that P is not equal to NP, right? It's probably the biggest problem in theoretical computer science, and we don't know. What we do know is a very interesting fact about NP, which is that there are NP complete languages. And what that means is that if you have any NP language, then and a statement that fires an instance in the language, then that can be reduced to an equivalent statement that there's a phi prime, which is in this NP complete language. Any NP language to an NP complete language. And for all the examples I know of NP complete languages, they're also matching translations of the witnesses. So if you have like a witness in an NP language, then you can also reduce that to the NP complete language and give you a witness for the same reduced instance in the NP complete language. And NP completeness is super powerful from a theoretical perspective, right? Because it shows that if you have a zero knowledge proof for an NP complete language, then I have a zero knowledge proof for any language in NP, right? Because the prover that wants to convince the verifier could just reduce the instance and the witness to a matching instance and witness in the NP complete language, and then run the zero knowledge proof on that. Right? And the verifier can also just take the instance in the original instance, reduce it to an instance in the NP complete language, and then do the zero knowledge verification of that proof. So what it shows is that if we have zero knowledge proofs for an NP complete language, then we can do zero knowledge proofs for any language in NP. Okay, and indeed there are zero-knowledge proofs for NP-complete languages. So zero-knowledge proof for circuit satisfiability, for SAT, for having graphs that have a Hamiltonian path that touch all nodes once. So in general, we will formulate that zero-knowledge proofs as saying, okay, we have a statement which is that here's an instance that belongs to a language where this is an NP language. And then the claim is that the prover knows a witness such that to so like testify to that. Now I want to say that so I also talked about special purpose cases, right? Do we have like a hedge fund or a exchange that is solvent, or have we encrypted a valid vote, or anything like that? And those special purpose statements are also very important. And the reason is that sometimes it's just much more efficient to give a direct zero-knowledge proof rather than going through an NP reduction, right? Because it can be expensive to do that reduction. So you see active research both on doing special purpose statements. Okay, so we're going to talk about how to develop zero-knowledge proofs. And I want to start with saying that often zero-knowledge proofs, they operate in some sort of like real-world setting where the prover and the verifier have a predefined setup. Okay, so maybe they already agreed that, well, we're going to use this prime order group because NIST developed it, right? Or maybe they agree that we're going to be using this hash function. Maybe it's SHA-256, and it's a very popular hash function. You can also have zero-knowledge proofs where there's no setup at all, that they just get going, okay? But sometimes setup can help you get a better efficiency or better security. Generalizing this, a very common model for a zero-knowledge proof is to say that we have a common reference string, okay? And what we imagine is that there's some trusted source that generates a string of, say, a string of bits and gives that to the prover and the verifier. And it varies depending on the setting you're operating in, whether, how we imagine that string to come about. So sometimes we imagine it's a uniformly random string. Okay, sometimes we imagine it's a structured reference string. Okay, so it's selected according to some specific distribution. Okay, and if it's selected according to some specific distribution, again, it may be that you can verify it has this distribution, or maybe you cannot verify that it has this distribution. So that's all. And some of them are more plausible than others, more trustworthy than others, right? So if you need a uniformly random string, right, you could imagine, looking at fluctuations in sunspots people have suggested, right? And presumably nobody can influence the sun. It's plausible that you actually get something that's uniformly random and not influenced. If you need a structured reference string, right, then there's a question of, how is it selected according to that distribution? And maybe you need to run a multi-party computation protocol to generate a common reference string with this particular structure, right? And then you're basing some trust in this multi-party computation protocol. So for the purpose of this presentation, I'm just going to assume that whenever we have a setup, then that has been generated in some trusted way. And then Carla is later going to talk about how we can remove some of that trust and make that more realistic to assume. Okay, so now we want to prove statements. In general, I'm going to think of zero-knowledge proof as working for a efficiently decidable ternary relation R that may depend on a setup, an instance, and a witness. Okay, and I talked before about NP, right, where you only had an instance and witnesses, and of course that's just a special case where this relation ignores the common reference string. Okay, so a statement is going to be specified when verifier, and then the setup and an instance and a claim that there exists some secret witness such that this triple is in the relation. And I'm going to write these statements as just a claim that this instance belongs to this language defined by the relation. Okay, so let's give some syntax here, right? So then how do we define a proof system, right? And you need to specify, whenever you develop a proof system, you need to specify three things. How do you expect the setup to be generated? Or more generally, how do you expect it to, what kind of properties do you expect it to have? And then how's the prover going to work and how's the verifier going to work? And I'm going to use this angled bracket notation here to indicate a protocol where the prover and the verifier may interact with each other. And at the end, the verifier terminates and either accepts the proof or rejects the proof. Okay, and the prover has access to the setup, the common reference string, and the instance and the witness, right? And the verifier has access to the common reference string and to the instance, but does not know the witness, right? So there's something interesting to convince the verifier about here. Okay, so recall Goldwasser, Micali, and Rakoff, they defined zero-knowledge proofs as having three properties, right? Completeness, that if both the prover and verifier are honest, and the prover has a witness, then the prover can actually convince the verifier. Okay, and the different variations of that, so it can be perfect completeness, statistical completeness, or computational completeness. And let me just talk about perfect completeness because that's the most common variation. Okay, so perfect completeness says that if you have an honest prover and an honest verifier, right, and the prover knows the witness, then it should always be the case that the prover convinces the verifier. Okay, so assuming that the setup is generated correctly like this. Okay, so we can look at this probability of this experiment where we run the setup, get a common reference string, we give it a worst case instance with a matching witness, so it's really a true statement, okay? And then we run this interaction between the prover and the verifier. And at the end of the day, the probability that the verifier should accept should be 1. So there's never any failure here. You can also relax this definition and still get some very useful zero-knowledge proofs. Okay, so statistical completeness just says that, you know, there's overwhelming probability that the prover will convince the verifier. Okay, so imagine you have a worst case statement, maybe some unbounded adversary. It's sort of like problematic, but with high probability, the prover is going to convince the verifier. And then you can have computational completeness, which just says it's really hard for computational bounded adversary to find the true statement for which the proof system fails. But I think for completeness, it's most common that you see proof systems that are either perfect complete or sometimes statistically complete. Okay, so let's move on to soundness. Okay, and here we're trying to protect the verifier. So we imagine there's a a cheating prover that tries to convince the verifier some false statement is true, right? And again, you could ask for perfect soundness, right? Which would say that a cheating prover could never convince an honest verifier of a false statement, right? And again, assuming here that the setup is honestly generated. So you would say this, you would compute this probability that if you compute an honest setup, and then the probability that an attacker convinces a verifier should be 0. And then you can relax that and say, well, it's very unlikely to convince an honest verifier, right? So then, we accept some small error probability, but in general, it should be very hard for an attacker to convince a verifier. And then you can relax that even more and say, well, okay, maybe we don't care so much about what a computational unbounded attacker can do, right? I just want to protect myself against a computational bounded cheating prover, right? So assuming that cheating prover only has the accumulated force of the computers of the internet, then the cheating prover cannot convince me of a false statement. Okay, and it's interesting to think about like this trade-off between security and efficiency, right? So why wouldn't you always want to get perfect soundness and get the strongest security guarantee? And the reason is that you can actually, if you relax the requirement for soundness, you can get better efficiency. And indeed, if you want to have like super efficient proof systems that have very low computation, then there's some indications that you may actually be forced to settle for computational completeness. Okay, I should mention here that sometimes people distinguish between perfect and statistical soundness and call that a proof system. And then computational soundness, they use the word argument system. Okay. So what's computational soundness? Okay. There are many variations of both soundness and zero knowledge. Okay. So and I want to take one step into the definition jungle and talk about proofs of knowledge, right? So informally, a proof of knowledge shows that the prover knows a witness for the statement. Okay, so if you remember, we had this example I gave before that you have an instance n, and the statement is that the prime such that n is the product of p and q. And if you give a standard zero knowledge proof, then it will just demonstrate that n has 2 prime factors, but it wouldn't actually show that anybody knows these prime factors, and maybe it's actually a much easier statement to determine, right? Maybe it's easy to determine the number of prime factors n has, but not what those prime factors are. So if you have a proof system that has knowledge soundness, then it would actually demonstrate more. It would demonstrate that, if a prover can convince a verifier, it's because we could actually extract that witness from the prover and write it down. Okay. And that's a stronger statement, right? Now it says, okay, the prover says, I know the factorization of n, right? And maybe the verifier thinks that's really amazing because it's one of the RSA challenges. Okay, so whenever you have a proof of knowledge, that's stronger than just standard soundness, right? Knowledge soundness implies the prover knows a witness, and soundness just says there exists a witness. Finally, part of the definition steps here is zero knowledge, right? So intuitively, the idea is that a proof should not reveal anything but the fact that the statement is true. And the way we typically define that is through simulation. Okay, so in this picture here, I illustrate that by saying that a verifier could have simulated the proof without knowing the prover's witness, okay? And if you can simulate everything, then you're not getting anything more from actually engaging with the proof. So let's dig into this a little more. There are many variations of how you can simulate, okay? So let me just give you one example that appears quite often in non-interactive zero-knowledge arguments, okay? So you define, when you want to prove that something is zero-knowledge, you will have to define how is that simulation run, okay? And there's a simulator algorithm that generates a setup, okay? And so it generates a common reference string sigma, but also associated that with a simulation trapdoor tau. Okay, so it's a tweak on how we do the setup, and now there's something extra coming out, this simulation trapdoor tau. Okay, and then there's a way to simulate proofs, okay, and that simulator does not know the witness, but it knows the simulation trapdoor, right? And then interact with an honest verifier and may accept or reject. Okay, and it may seem a little odd, why do we have this simulation trapdoor? Okay, but let me make clear, it's clear that the simulator needs to have something to simulate, right? If you could have nothing extra and you could simulate, well, then you could just, whenever you have a statement, you could just run the simulator and generate proof, and you could break soundness. Okay, so we want it to be the case that in a real normal setup and a real normal execution of the proof, it should not be possible to create a proof for a false statement. Okay, and therefore, if it's suddenly possible to simulate proofs, then it must be because there's something extra. The world is set up in a different way. Okay. Now, the reason we can justify that is because it does not leak information about the witness, right? Because this simulation trapdoor has nothing to do with the witness. Okay, so it's clear that here in the simulation, yeah, well, we're constructing a convincing proof to the verifier, but it does not show anything about the witness. Okay, and what could a simulation trapdoor look like? So remember, I talked about having a common reference string. Okay, maybe that common reference string has an encryption of 0, right? And then we have strong soundness guarantees, and then maybe when we do the simulation, instead we embed a 1 in the ciphertext, and that's sort of a trapdoor. And if you know the opening of that commitment to 1, then you can simulate things. So typically that's the kind of way we do it, right? And then we want to make sure that in the real world there would never be such a simulation trapdoor. Okay, so let me just hint at how do we define simulation to be good? Okay, so here's two games, and in the top half we have a game of a real proof, right? So imagine you have like a normal setup. The prover has a witness, engages in a proof, and tries to convince this malicious verifier. Okay, and in bottom half we have the simulation. So imagine you have a simulated setup, and the simulator uses the simulation trapdoor to engage with the verifier. And in both cases, the verifier will output a guess. Am I in a world where I'm interacting with real prover, or am I in a world where I'm interacting with a simulator? And we say it's a good simulation if this verifier cannot guess which of the worlds it's in, right? So we want it to be indistinguishable whether it's running against the real prover or against the simulator. Okay, and again, zero knowledge can, just as the other ones, be perfect, statistical, or computational, right? So perfect is if the simulation is identical to real proof. And statistical is if it's really hard for a computationally unbounded evil verifier to tell whether it's running in simulation or a real proof. And computationally, if this verifier is computationally bounded and cannot distinguish whether it's seeing a real proof or a simulation. Okay, and again, you have these trade-offs, right? Of course, it would be nice if everything was perfect zero knowledge, but maybe you pay a price and you cannot get as good soundness, for instance, if you have that. And typically, there's this trade-off: either you can get statistical or perfect soundness, but only computational zero knowledge, or you can get perfect statistical zero knowledge, but only computational soundness. Finally, I want to mention that there's some other useful definitions of confidentiality that are weaker than zero knowledge. So one of them is witness hiding, that if you see a zero knowledge a proof, then it does not help you to compute the witness. Okay, and in particular, if it's zero knowledge, it leaks nothing about the witness, and therefore it would not help anybody to compute anything. Another notion is witness indistinguishability. So imagine that many possible witnesses the prover could have for the statement being true. Those witnesses the prover has, and it is clearly a weaker notion than zero knowledge, right? Because imagine, for instance, you have a statement for which there's only one witness. Okay. So in that case, you could actually send the witness in the clear to the verifier, because it would not allow the verifier to distinguish between different witnesses, because there are no different witnesses, right? But clearly it would not be zero knowledge. You're leaking a lot of information. You're actually leaking the full witness.
Jens, sorry for interrupting you. Maybe we can have a short pause for a few questions from the audience.
Absolutely. I think this is good to have that.
Myself have a question, so can I ask?
Yes.
So do we have an example of zero knowledge proof, which is a zero knowledge proof, but is not a proof of knowledge?
I think the answer is yes, but I don't actually have a good example right on top of my head.
Oh, okay. Yeah, it's somewhat difficult to think how can somebody prove that I have a witness, but without proving the knowledge. Okay, so from the audience, does anybody have any question? Everybody, anything is crystal clear so far? You can raise your hand and ask questions. Okay, so there seems that everything is very clear. Thanks for your nice presentation. So
do please interrupt me, because I don't see anybody raising their hands, because I'm just looking at my slides. Okay, so finally, I want to talk a little about performance of zero knowledge proofs and how to measure that, right? So the most common thing people look at is the communication. So you could measure that in the number of bits that the prover sends to the verifier and the verifier sends to the prover. Then people care a lot about, how much computation does the prover have to do, right? In particular, you're concerned about the time, so you may measure that in the number of seconds on whatever equipment the prover has. And you would also care about, computation that the verifier does. And then you can be interested in the round complexity. How many messages do you need to send back and forth between the prover and verifier, right? And if it's a slow connection, of course, that will impact the latency of the zero knowledge proof. And state of the art right now is that you can actually have like ridiculously little communication, very efficient verification, and non-interactive proofs where you only send one message and that's it. Okay, the price you pay for that is in the proof of computation, and a lot of research effort right now is going into trying to also reduce the effort that the prover puts into the zero-knowledge proof. Okay, but there could be other things that people care about, and indeed people have cared about, right? The size of the setup, the computation going into the setup, the memory consumption that the prove and verify has, the parallelization of their computation, energy consumption, and so forth. Okay, so I want to stress this thing about round complexity, right? So, so you can have interactive zero-knowledge proofs where the prover and verifier send messages back and forth. So the prover sends a message, the verifier sends a challenge back, and the prover responds to that challenge, and so forth. Or it could be non-interactive. The prover just sends a proof, and that's it. Now the verifier can verify. And I think this is a very important distinction, because a non-interactive zero-knowledge proof also has some properties that interactive proofs don't have, right? So you can actually, if it's non-interactive, you just get a proof. That's it. You can copy it and you can show it to somebody else, right? If it's interactive, you know, and you show them some transcript, right? They okay. And now you may ask, okay, so if it's best to have non-interactive zero-knowledge proof, why do we even care about interactive zero-knowledge proof? And the reason is that it's typically easier to construct interactive zero-knowledge proofs. Okay, but there's a very nice trick that sort of like can split that process in two. First, you construct an interactive proof system, and then from that you convert it into a non-interactive proof system. So this works for an interactive system which has this, what is known as the public coin property, right? And public coin means that there's a proof system where the verifier only sends uniformly random challenges back, okay? And if those challenges are big enough, let's say 256-bit strings, then you can use the Fiat-Shamir heuristic to make the proof system non-interactive. And the way that works is that you use a hash function to compute the challenges, right? So imagine you have an instance, the prover has sent some messages. You just hash all of that, and you use the hash value as the verifier's challenge, right? And now there's no verifier anymore, right? Because you can compute all the challenges using a hash function. And intuitively, this makes sense because a cryptographic hash function, well, what does it do? It takes some inputs and it tries to mess them up and mangle them as much as possible and give you some random looking output. So that's the Fiat-Shamir heuristic, where you take, and it's important here that the proofs should be public coin, right? And then it just generates these, what is supposed to be uniform random challenges, that just uses hash values and sends that, uses that. And now the proof can just compute full transcript.
I have also another question, but I think also a difficult one. So when we say that zero-knowledge proof is a public coin, so we say that the coins are uniform, and also we say that so this uniformity is not really a big deal. So if the verifier selects the random is according to another distribution, it can typically be distributed from the uniform coins too. But I think what we really want is that the verifier doesn't keep some internal state, which is hard to compute from the public coins, right?
Yeah. So I guess there can be different reasons for that, right? And you may not be able to distinguish. I mean, maybe it's, you know, these supposed public coins are not real public, but they're generating some pseudo-random way where, you know, the verifier has some secret, right? So so indeed, the main concern is that, you know, well, so this is sort of like, what if the verifier deviates from the protocol and doesn't actually send something that's uniformly random. But you could also, in principle, and again, I don't have any good examples of that, right? But you can imagine proof systems where you actually, it really is important that the verifier has some secret, right? Maybe the verifier sends a ciphertext of some sort. The prover does something with that ciphertext, and now the verifier decrypts that ciphertext and checks something. So you can find examples of non-public coin. Common type is public coin proof system.
Okay, so exactly my question was whether it could be helpful, or that the verifier can cheat by keeping an internal state, and you said that you don't have an example in mind. Okay,
and that would be exactly one concern you could have.
Since you have another question, Jens, sorry.
Sure.
I mean, maybe you could let me just unmute this speaker. Okay, you can ask your question, Neha. Just please first unmute yourself. Yeah.
Hello, am I audible?
Yeah. Hey.
Hello, sir. So actually, I want to know, like, not exactly with this slide, but I want to know what is security parameter. Like, how can we decide this is the security parameter for this or any cryptographic protocol or algorithm?
Right. Okay. Yeah. Right. So a security parameter is something we use to parameterize cryptographic protocols, and the intuition is the larger the parameter, the more secure it should be, right? So, for instance, you have SHA-256, SHA-512, SHA-1024, right? And the idea is that the larger the number, the stronger the hash function.
Okay. Okay, so by that we mean the more the security parameter, the more stronger our protocol, or
exactly.
adversary cannot guess the exact bits.
Yes.
Okay. Thank you.
Okay. Okay. Okay, so I want to briefly mention what is the ultimate performance we could hope for, right? And there's a lot of interest in something called ZK SNARKs, okay? And SNARKs stand for Succinct Non-Interactive Argument of Knowledge, right? So it's a proof system which is non-interactive, okay, which is nice. It's a proof of knowledge, which is also nice, okay? And then it's succinct, okay? And succinct means that the proof system has very little communication, okay? So it's just a few kilobits or something like that. And we can actually do proof systems where the proof is, it really is just a couple of kilobits or something in that order. And the verification may also be very efficient, right? I mean, if the proof is very compact, you could imagine maybe the verifier is also really super efficient, okay? And it's very useful if you have like a language which has complex statements with a large witness and requiring a lot of computation to verify. Then it's really nice if you have a SNARK, right? Because you can create very small proofs and it's very efficient to verify, even though it's this kind of complex things, right? And people actually use that a lot, right? So there's something called zero-knowledge rollups in the blockchain space. And the idea is roughly here, look, say, here's a block hash, a Bitcoin or some other blockchain. And then, I'll give you a proof that everything is the result of a valid computation. Okay, and now instead of going and verifying the whole Bitcoin blockchain, now the verifier can just verify that proof. Okay, takes a few seconds to verify and then says, sure, okay, this is like, this hash is. So it can really save the verifier a lot of work. Okay, there's a bit of nuances here, right? So one thing that's interesting is the snarks are actually also interesting for language in P, right? So in principle, languages in P can be verified, but it's in polynomial time, right? And that may still be too expensive. And with snarks, you can actually get sub-polynomial, sublinear time to verify things, right? Because you can just give a proof and then the verifier verifies that proof instead of actually verifying the statement itself. And in those cases, you only need completeness and soundness, right? I mean, if it's an instance in P, then you don't need a secret witness or anything like that, right? I mean, the verifier could, in principle, verify everything himself. So you may only need to actually care about completeness and soundness. And in the literature, people tend to mix those terms a little back and forth, right? And I don't mind so much, but if you really care about zero knowledge, I would say you should say ZK snark. And if you do not care about zero knowledge at all, I think using the word snark would be appropriate. One thing that's interesting with these succinct proofs is it does point a little towards when you do research in zero knowledge proofs, what is easy and what's not easy, right? A succinct proof is really small. It's only a few bits. So it can, just information theoretically, not leak so much information about the witness, right? So usually what's really hard to get is soundness, because you have to sort of get soundness from just a few bits. And add a little masking, and then you're done and you have zero knowledge. Okay, so I want to shift gears now and actually show you some zero knowledge proofs, and hopefully that will also help crystallize all these definitions. Any questions so far? Okay, so I want to talk about Sigma protocols, which is a very used type of zero knowledge proofs. And it's basically a 3-round zero knowledge proof, okay? So we'll have some statement, some specified by an instance phi, and a claim that it belongs to the language. And the prover has a witness. And the structure is that the prover sends an initial message A, gets back a random challenge, all right? So this is a public coin proof. It's just a uniformly random challenge. And then sends an answer to that challenge. And then the verifier looks at the whole transcript and accepts or rejects. Okay, so the verifier really doesn't have to do much along the way in the proof, just send random challenges and record everything. It's only in the end that the verifier actually does some interesting verification. Okay, and let me use through here an example with a cyclic group. So let P be a prime, ZP the integers modulo P, and G be a cyclic group of size P, right? So what that means is that if we have a group element G, then G to the A and G to the multiplied with G to the B would and everywhere, I'm not going to write that explicitly, but everywhere you should think whenever you see A plus B or A times B, that it's always reduced modulo P. Okay, and we also have double exponentiation property. If you have G to the A and you raise that to the B, then you get G to the A times B. Okay, and the known, very well-known cryptographic problems and assumptions associated with this, right? One is the discrete logarithm problem, if you're given G and G to the A, then the goal is to find the discrete logarithm alpha. And in general, what we want to assume is that if we have a suitable group G for cryptographic purpose, then the discrete logarithm problem is hard, right? So given G and G to the random alpha, it's actually going to be very hard to find alpha. And there's also
sorry, Jens. There is a question here. Somebody has asked if a proof in NIZK can be used by verifier to convince a third party. So
exactly, that's so like the reason why it's very interesting that it's non-interaction zero knowledge, because you can just copy that proof and send it to a third party, and then they can run the check themselves. That the assumption is that the third party has to trust the setup as well, but typically that's the setup we have.
Okay, thank you.
Okay. Okay, another very well-known cryptographic problem is the decision Diffie-Hellman problem, given G, H, G to the alpha, H to the beta. Try to guess if alpha is beta or they're different. Okay, so I want to show you a Sigma protocol that something is a Diffie-Hellman tuple. Okay, so what we have is an instance, G, H, U, and V. And the prover has a witness alpha that U is G to the alpha and V is H to the alpha, right? So here they have both the same discrete logarithm alpha. But according to the decision Diffie-Hellman, the verifier may not know that, right? I mean, because the verifier cannot tell whether it's the same alpha in U and V or it's a different alpha and beta. Okay, so the way the proof works, so now the prover wants to convince the verifier that that's actually the case. And the way the proof works is the prover picks some randomness R and then computes A, which is G to the R, and B, which is H to the R, right? And sends those two group elements to the verifier. And the public coin verifier just sends a random challenge X and a random element ZP. And now the prover computes Z, which is alpha X plus R, and sends that to the verifier. And the verifier runs two checks, okay? Checks that U to the X times A is G to the Z, and V to the X times B is H to the Z. Okay, so now I've described, so like, you know, how the prover works, how the verifier works, and the next goal then is to show that it's a knowledge proof system. So I need to convince you that it's complete, that it's sound, and that it's zero knowledge. Okay, and completeness is fairly easy because you just plug in numbers and see the verifier will actually accept whenever the prover has followed the protocol. So what is U to the X times A? Well, U was G to the alpha. A was G to the R. So we get G to the alpha to the challenge X times G to the R. And that's G to the alpha X plus R. And alpha X plus R, that was exactly Z. So that's G to the Z. So the first verification check passes. And exactly the same for the second verification check. So that shows we have perfect completeness in this protocol. An honest prover will always convince an honest verifier. Okay. Let me then jump to zero knowledge. And here I'm not going to show zero knowledge. It's not even clear that it that it's honest verifier or not. And what that means is just that I'm assuming here that the verifier actually sends a uniformly random X and not some maliciously generated X. Okay. Right. Okay. So the question here, so I'm removing the prover here. The question is, can the verifier simulate everything that the verifier sees? Okay. Without knowing the witness. Okay. So the verifier would, in a normal proof, see two group elements A, B, pick a random X, see an answer Z, and then check these two verification equations. And the trick here to show that it's honest verified zero knowledge is that we can actually change the order in which we are doing these things, right? All we need to simulate is this whole transcript, but we don't have to do it the way that it's done in a real proof, right? So what we do is first we pick X, the challenge that the verifier selects, right? That's just a uniformly random element. So we've just picked that a little in advance. And then afterwards, we pick Z, and that's also we just pick it uniformly at random. And then we pretend that, A and B were the ones that worked actually like that. And we can actually compute that from the verification equations, right? If you know X and Z, then there's just one unique A that matches the verification equation and one unique B that matches the verification equation. So we just compute them so they would actually work in the verification equation. So now we've simulated the whole transcript, and the idea was that, well, an honest verifier is just going to pick a random challenge and then look at the transcript in the end and run this verification equation. So we just create the transcript in a different way. And the next question is this a good simulation? Okay, so let me convince you that it really looks exactly like a real proof. Okay, and the thing to note here is that both in the simulation and in real proof, X and Z are uniformly random, right? X is uniformly random because that's what an honest verifier chooses X like. And Z is uniformly random because in a real proof, you have this R, okay, and Z is something plus this random R, okay? And because R is uniformly random, therefore Z is also uniformly random. So in the simulation, clearly X and Z are uniformly random. In a real proof, they are also uniformly random. And then both in a real proof, it has to satisfy the verification, and in the simulation, it has to satisfy the verification equations. So A and B are uniquely determined by X and Z. Okay, and that proves that real proofs, these transcripts in real proofs, look exactly like they do when you simulate. Okay, and therefore it's honest to verify zero knowledge, right? You're not learning, the verifier learns nothing from the transcript, right? Because the verifier could construct the transcript himself. Okay, and remember I said that there's some extra power you have to be able to simulate, right? And the extra power is that the verifier does not need to simulate the transcript in the same way as in a real proof, right? So you actually know the challenge first, and then you match everything to that. Whereas in a real proof, the prover would first see A and B and then get the challenge. And then let me go to soundness, okay? And I'll show it has statistical soundness. So there's some very small probability that you can cheat, but it really is very small. It's 1 over p. Okay, so imagine we have an evil prover. Imagine that u is g to the alpha, v is g to the beta, and alpha and beta are not equal to each other. Okay, and what the verifier just sees is, well, you see two group elements A and B, send a random challenge X, and see some answer Z, and then plug it into these verification equations. So what happens here, right? So imagine that, it's a false statement. So the discrete logarithm alpha and beta are different. Okay, and it's very clear that when you see group elements A and B, then A is g to the r for some r that the verifier doesn't know, and B is h to the s for some s that the verifier doesn't know. And at this point now, the verifier sends a random challenge to the prover. Okay, and we need to have both of the verification equations satisfied, right? So ux times a has to be equal to g to the z. And the implication is that z has to be alpha times x plus r. And also, the second verification equation says v to the x times b has to be equal to g to the z. And the implication is that z has to be equal to beta x plus s. Okay, and the key thing to notice here is that if alpha is not equal to beta, then that's actually defines that z has to be in two different lines. Is the beta x plus s. And the verifier chooses x hat uniformly random, right? And if you have two distinct lines, it's very unlikely that this random choice of x hits the intersection of those two distinct lines and is just the place where, you know, the same z works in both equations. Most likely you will have some different point where you get like two different values z, and then the prover is stuck and cannot get just one z that matches both equations. Okay. Any questions to this proof of equivalent discrete logarithms? Okay, so I hope that was sort of like an understandable example. What I want to do now is I want to show you a few more Sigma protocols, and so like I don't want to go all the way to snarks, but I want to hint at how come that it's possible to go all the way to, you know, having sublinear, very succinct proofs. Okay, so this was not a succinct proof, right? The statement is 4 group elements. The proof is a couple of group elements, a couple of field elements, right? So it's sort of like comparably the same order of magnitude. Okay, so so let me first jump to an exercise here. So I want to give you an even simpler problem, okay, protocol, a Sigma protocol that you have a discrete logarithm. Okay, so here the instance is G and U, and the witness is an alpha, and U such that U is equal G to the alpha, right? So the prover knows the discrete logarithm of U. And well, so first of all, observe here that in some sense this is a silly proof, right? If we are thinking about, you know, just whether it belongs to the language, right? Because what is the claim? It is that this group element U has a discrete logarithm alpha with respect to G. But, you know, if G is a generator, then any group element U has some discrete logarithm with respect to G, right? So soundness trivial. What is interesting, though, is knowledge, right? Does the proof actually know that discrete logarithm or not? So this clearly distinguishes soundness from proofs of knowledge, right? From a soundness perspective, it's trivial. U has some discrete logarithm with respect to G, okay? From a knowledge soundness perspective, it's very interesting. Does the proof actually know alpha or not? Okay, so the proof works, and it's similar flavor as we just saw, right? So you pick R at random, you compute A, which is G to the R, and send that to the verifier. And then the verifier responds with uniformly random challenge. And the prover computes alpha x plus R as Z and sends that to a verifier, and the verifier accepts if Ux times A is equal to G to the Z. Okay, so the exercise here is to basically think about this one. Okay, so I would suggest you first check that it is actually complete. So it works if the proof is honest and the verifier is honest. Then check that it's zero knowledge, right? So can you simulate this proof without having the witness? And then finally looking at whether it has knowledge soundness, right? And a hint here is, imagine the prover has sent A, okay? And if the prover is going to be successful in convincing the verifier, then should be able to answer a challenge. And you know, maybe we could send it multiple challenges and answer many of those challenges. Okay, so that's the exercise. I'm going to flip back to the previous slide so you have, like, you can view the proof system, but I think it's good time to just take 5 minutes, think about this exercise, and so like get the notions of completeness and soundness and zero knowledge into your hands. Okay, So let's take 5 minutes for this exercise.
So thank you, Jens. So far, do you have more slides, or is this your last one?
Oh, I do have quite a few slides, yes.
Okay.
If that's okay. I may not make it through all of them, but I'll try to select so it sort of like fits. As far as I understand, I have 40 minutes more.
Yeah, but it's not problem. We can finish it earlier. So maybe meanwhile I can ask a question about mixed nets. So
Sure.
I know that you are known for having the most efficient mixed net, but how do you compare it with Douglas Wickstrom's mixed net? Or this is one question I have, and another one is that this context of internet computer or blockchain. So do you see any prospects?
Right. Okay. Yeah. Okay. So just a background to those who are listening to this and not familiar with mixed nets. So the idea with a mixed net is that you want to do anonymous broadcast of messages, and the way it works is that you encrypt messages, send them to a mixed server, and the mixed server mixes them up and outputs in permuted order, and you may do that in multiple rounds, and then you open all the ciphertext, but now because of all these permutations, you don't know who sent which message. And you can use zero-knowledge proofs to prove that these permutations are honest. So you're not just substituting a new ciphertext that nobody sent. And I have some constructions of zero-knowledge proofs for mixed nets, and Douglas has a zero-knowledge proof for mixed nets as well. And I think they're comparable in efficiency. So there are sort of like linear size proofs, and Douglas is that too. I think there's a bit of a trade-off sometimes between complexity and simplicity. So maybe Douglas's is a bit more simple proof, and mine is a bit more efficient. So I don't see sort of like a super big difference there, right? One big difference is that Douglas has an implementation of the mixednet in the verificatum protocol. So that's actually really nice, and done a lot of effort to make it secure and get reviews of it. And I guess another distinction is that then I've also looked at sublinear zero-knowledge proofs for mixed nets. So you can actually get proofs that are much smaller than the mix itself. And I think people have so I got it down together with my PhD student, Stephanie Bayer, to square root size, but people have gotten even further down to logarithmic size. But I think we're also in a situation where maybe it doesn't matter so much anymore, right? Because in either case, the communication complexity is dominated by these ciphertext, and you have to send them anyway. So whether you're saving a little bit on the zero-knowledge proof or not, I think is not quite that big a deal anymore once you're already down in the sublinear space. So does that answer your question about mixed nets?
Yeah, that was a very nice answer. Thank you. The second question was viewing voting in the context of blockchain.
Right, and I guess so. It's not something I've looked particular at. Right, people have suggested doing voting on the blockchain. Other people have suggested it's a really bad idea because things are public on the blockchain. But I think you could imagine doing some of the secure voting protocols on the blockchain. Just use that as a sort of like a bulletin board where you store the information. Everybody can verify that, and then you would get privacy from the cryptographic protocols. So I do think it's a feasible thing to do, but it's not something I've looked particularly much into. It should be said that we do quite a lot of voting on the internet computer, but it is non-private voting. But whenever you change the protocol on the internet computer, it actually goes through a vote, and then the vote protocol change is automatically implemented if it's voted through. Okay, so let's
continue.
Yeah, let's return here. Okay, so we had this exercise, and I hope you all had the chance to think about it, right? So here's my own answer. For completeness, again, basically you plug in the numbers and see u to the x times a is the same as g to the alpha to the x times g to the r, and that's g to the alpha x plus r, and alpha x plus r is z, so therefore the verifier accepts. And for zero knowledge, well, then you would need to come up with a simulation, and we can sort of like use the same trick as before. If we pick the challenge first and we know what challenge the verifier is going to send, then it's a lot easier to simulate. So we pick the challenge first, then we pick Z uniformly at random and compute the only A that fits into this equation. And in both cases, both in a simulation, the real proof X and Z are uniformly random, and then A is the only thing that fits in. So the distribution of simulated transcripts and real transcripts are exactly the same. Okay, and as argued before, soundness doesn't make much sense because, of course, U has a discrete logarithm base G. But knowledge soundness makes a lot of sense. And actually what it has, and what all Sigma protocols have, is something called special soundness. And the idea is that if the prover can answer two distinct challenges, then it's actually possible to extract the witness. Okay, so the strategy is roughly, we run the prover until the prover has sent the initial message. Then we clone the prover state, and then try many challenges. Okay, and if the prover can answer all of them, then it can only be because the prover knows W. And if the prover cannot answer any of them, then probably because the prover wasn't that likely to be successful to convince us and cheat us. This is also known, and this is a very important concept, it's sort of like a rewinding strategy. So the way people also think about this is, okay, we run the prover, see that it answers a challenge successfully, rewind it back to the state it had before, and try with another challenge. And if it answers multiple challenges, then we can extract a witness. So let's see how this extraction works if we have this particular proof system, this particular Sigma protocol. Okay, so imagine the prover has a good chance of convincing the verifier after sending this initial message A. Okay, so we just feed the prover a challenge X, rewind the prover, give it another challenge X prime, and if X and X prime are distinct and we get two satisfactory answers, Z and Z prime, then the claim is now we can actually extract the witness. Okay, so we have this verification, UX times A should be G to the Z. And for the second challenge, that would be UX prime to the A times A should be G to the Z. And if you divide those two equations with each other, then and do all the math, the A's cancel out, and you get U to the X minus X prime is G to the Z minus Z prime. And because X and X prime are distinct, then that means that U is G to the Z minus Z prime divided by X minus X prime. And with respect to base G, right? And that discrete logarithm is Z minus Z prime divided by X minus X prime. So the reason it's a proof of knowledge is that we imagine the prover, after having sent A, has some significant chance, epsilon, of convincing the verifier. Okay, if it had a very small chance, then it just was not unlikely to convince the verifier anyway, right? And we don't worry about it. But if it really had a good chance of convincing the verifier, then that prover would be, right? And in real life, it would never accept to answer two challenges, right? But we could imagine such a prover that was successful would be able, in principle, to answer multiple challenges, both X, but it's just uniformly random. So another uniformly random X prime, it should also be able to answer. And if the prover is able to answer multiple challenges, then we would be able to extract a witness from it. Okay, so I hope this exercise gave you sort of like a feeling for completeness and soundness and knowledge soundness and zero knowledge. Okay, so I have half an hour, and what I want to use that for is basically do a bit of a run through sort of like some more sophisticated Sigma protocols, and sort of like hint at why it is that we can get sublinear complexity and really efficient zero knowledge proofs. Okay, I should mention one thing. I did cheat a little bit because what you saw was honest verifier zero knowledge, right? The simulation assumes that we pick X uniformly at random. A malicious verifier might actually pick something that's not uniformly at random, right? So let me just justify that, and I'll justify it with a feature heuristic, right? So quite often when you have a Sigma protocol, the way you want to work is actually you want to use it for a non-interactive proof, right? So you would compute the challenge X as the hash of, say, the instance and the initial message. And what we assume when we prove that the feature heuristic gives a secure and non-interactive zero knowledge proof is we typically assume that the output of the hash function looks random. So we say that we're in the random oracle model, where we model the hash as a completely uniformly random function. Okay, and if the hash function is a uniformly random function, then X is indeed uniformly random. We sort of like get the true zero knowledge for free from that random oracle model. So because the verifier is a hash function, okay. If you actually have an interactive protocol, there are also tricks you can do to make them real zero knowledge, right? And one trick, for instance, is do some coin flipping to decide between the proof and the verifier to decide what the challenge X should be. Okay. Okay, so let's see. So one thing I wanted to show is that we can do Sigma protocols for NP-complete problems. Okay, and one very popular type of statement is that that of defined by instances defined by arithmetic circuits. Okay, so here's a circuit. It has some addition gates. It has some multiplication gates. All of them over integers modulo p. And the claim is that, well, we have some there exists some inputs such that it would output 0, for instance. And it's a very popular type of statement. First of all, you can show that arithmetic circuit verifiability is NP complete, so it means that we have general purpose zero knowledge proofs. But it's also natural, right? I mean, cryptographers love doing finite field arithmetic, right? So it's sort of like, it speaks very naturally to cryptography done in practice, and you may be able to avoid expensive NP reduction because you're sort of like doing what you wanted to do anyway in cryptographic protocols. There are variations of arithmetic circuit satisfiability. So you could, some proof systems are for a fixed arithmetic circuit, and what you vary is just, some of the values are fixed to some constants. Others allow you to, choose the arithmetic circuit. Okay. So let's see. So in order to prove arithmetic is satisfied, I'll use a commitment scheme very quickly. The intuition behind a commitment scheme is that the prover or the sender can commit to a message. So imagine taking the message, putting it in a box, sending it to the verifier. Right now, it's binding. The prover cannot change her mind about this message. Okay, it's also hiding because it's inside the box. The verifier doesn't know what the message is. But the prover may open the commitment, say send a key. Right now, the verifier can open the commitment and check what the message was. Okay, and one way to create a commitment scheme is basically use encryption, right? And then you can later on reveal here's the plain text and here's the random is used to generate the ciphers. Another way is something called a commitment scheme. And very popular commitment scheme is the Peterson commitment scheme. And in the Peterson commitment scheme, you have a setup, which is a group of prime motor P, and generators, random generators G and H. And to commit to a message, you pick a randomness R, and then you compute the commitment with G to the M, H to the R. And the opening of the commitment then is the message and the randomness. And once you send the opening to the verifier, then it's very easy to check that this was indeed the stuff that was committed to. Okay, so I'm not going to do this as an exercise because I don't have that much time, okay? One nice property of this commitment scheme is it's homomorphic. If you take a commitment to M and a commitment to M prime, and you multiply those two group elements, you actually get a commitment to the sum of those two messages. Okay, and that's not too hard to see. You basically just take a commitment to M and with a randomness R, multiply that with a commitment to M prime, message M prime and R prime, right? And if you multiply those G to the M, H to the R with G to the M prime and H to the R prime, they get G to the M plus M prime and H to the R plus R prime. The commitment scheme is perfectly hiding. It reveals nothing of the message. And the reason for that is that you have this randomness R, you pick at random, right? And if you pick R at random, then H to the R is just a random group element. So no matter what M is, the commitment will just be a random group element. Okay, and then you can show that it's also computationally binding. So if you can open a commitment in two different ways, okay, then you would actually be able to compute the discrete logarithm of H with respect to G. Okay, I should mention that, of course, Peterson commitments, as anything else based on cyclic groups, is broken by quantum computers. But part of the reason I'm formulating this way is that you do actually have homomorphic commitment schemes also based on lattices, and you can also based on hash functions and so forth. So there's a lot of this stuff that also applies in the post-quantum setting here. So I'm trying to be general and cater to the post-quantum. Okay. Okay, so very briefly, you can give a Sigma protocol for knowledge of an opening of a commitment, and it follows pretty much the pattern we've seen before, okay, with group elements. So here the trick is, okay, so let's say we have a commitment C, and we want to prove that we know the opening of that commitment. Well, you would generate a commitment to a random chosen lib B and send that to the verifier. The verifier picks a random challenge, and then you compute an opening of this. You compute F, which is the message times the challenge plus this random B, and Z, which is the randomness in the commitment times X plus randomness in your new commitment, and you send that back to the verifier. And then the verifier checks that C to the X times A is a commitment to F and Z. And again, completeness and special soundness on verified zeros is very much like we've seen before in the discrete logarithm setting, right? It's sort of like the same linear algebra that we're using. Okay, so what is the strategy to prove that we have an arithmetic circuit satisfied with this? So suppose we have a circuit, we want to prove that it outputs V. Okay, and the strategy is we will use Peterson commitments to commit to every wire, right? And because the Peterson commitment is hiding, those commitments are not going to reveal anything about the witness. Okay, for public values, so V in this example is a public output, it has to be V that the circuit outputs. There you can just use 0 to commit to that V, and it knows V is part of the instance. It knows 0 as the randomness, and then it can just recompute the commitment, check that. Okay. Now, remember, Peterson commitments are homomorphic. So whenever we have an addition gate, we don't actually compute ourselves the commitment. What we do is we just take the commitments to the two inputs and use a homomorphic property of a commitment scheme to commit to the output wire. And the only remaining problem is, okay, now we have a bunch of commitments to all sorts of wires. We already have the homomorphic property guarantee that the addition wires are satisfied, right? And we can check all the public values are correct. What we don't know at this point is that if you have two input commitments to a multiplication gate and a protocol for a multiplication gate, okay? So you have three commitments, you have openings to those commitments, and the claim is that the committed wire values W1, W2, W3 satisfy this multiplicative property. And for the sake of time, I think I'm going to skip sort of like the intuition behind the construction here, but just point out that it's a fairly simple scheme, right? It sends 2 group elements and 4 field elements and gets the verifier to accept that indeed this product is satisfied. Okay, and the main trick here is that in these verifications that you check, what you really check when you do so like the computations of all these values, what they mean is that inside you have this W1 times W2 minus W3 times X, and something else should be 0. And it's very unlikely over the choice of this random challenge X that it's 0, unless indeed W1 times W2 minus W3 is indeed 0. So that's how we catch a cheating prover. Okay, so what's the cost of this? It's actually not too bad. It's sort of like linear in the circuit, right? So, you have wires, you commit to the values in the wire, so that's 1 commitment per wire. For the public values, it's already known in the instance, so they come for free. The addition gates, it's easy to multiply 2 input commitments together to get the output commitment, so that's also for free. And then for every multiplication gate, we paid like 5, 6 elements, right? So overall, if you have an N-gate circuit, then you can prove arithmetic circuit satisfiability with O of N group and field elements. Okay, so this shows in general for an NP-complete problem that here is a sigma protocol that you can use to prove that this arithmetic circuit is satisfied. Okay, and the really interesting question then is, okay, can we do more efficient than that? And the answer to that is yes. And I want to briefly give you some intuition of why the answer to that is yes, and how you could do it even more efficiently. So instead of proving one thing at a time, you prove many things at a time, and sometimes you can do that more compactly. Okay, so I'll give you an example of how to batch together a proof of knowledge for many openings. Okay, so instead of having 1 commitment as the instance, now we have an instance that has T commitments. Okay, and the prover knows all the openings. And what the prover does is basically the same as the earlier opening sigma protocol, okay? But it just sort of like batches things together, so you actually have less elements in the end, okay? So the prover picks B and S at random and commits to B with randomness S and sends that to the verifier. So that's 1 commitment sent to the verifier. The verifier gives a uniformly random challenge X. And now the prover computes a little more complex sums based on this X. So instead of having just a linear combination, now it's sort of like a polynomial in X. Okay. But at the end of the day, F and Z are just field elements, so it sends 2 field elements to the verifier. And the verifier does a more complicated check. A times the product of the commitments raised to powers of X is a commitment to F and Z. Okay. But it's still, just one equation that the verifier has to do. Okay. Now, if T was equal to 1, this was exactly the same Sigma protocol for knowledge of an opening as we had before. Okay, and we know there that if the prover could answer 2 distinct challenges, then we could combine the verification equations and open. That if you have a larger T, what you need is you just need answers to more challenges. If you have T plus 1 challenges that could be answered, then you can actually, for every commitment, do combinations of answers to those challenges and get their openings. So like a little akin to the fact that if you have a degree T polynomial and you have T plus 1 points on that polynomial, then you're able to interpolate and figure out the whole polynomial. Okay, so if you have 2 points on a degree 1 polynomial, a line, right, then you can determine the whole line. If you have a degree T polynomial, T plus 1 points in that polynomial, then you can determine the whole polynomial. And that's sort of like what intuitively happens in the exponent that allows you to find the openings of every single commitment. Okay, so what do we have now? We now have actually a fairly large instance of size T, right? But the communication in the proof itself is actually much smaller, right? You just set one group element and a couple of field elements from the prover side. So that gives us a hint that, communication may actually be much smaller than the statement that you want to prove. Okay, now people could complain and say, well, the instance is still big, right? And the verifier still has to do quite a lot of computation. That's linear in T. So can we do even better? And the answer to that is yes as well. So there's this generalized Peterson commitment where we just have some more group elements. And we can actually commit to many messages with one group element. Okay, so if we want to n, then we compute a commitment as h to the r times the product of all these gi's raised to mi. And it's exactly the same as a Peterson commitment, but now we've committed to a full vector of field elements instead of just one field element. Okay, and it has the same properties before. It's perfectly hiding, computation binding, and it has this nice homomorphic property that if you multiply commitments together, you actually get a commitment to the sum of the vectors, right? And that's really important because now one product of individual group elements, that actually gives you a check of like an addition of entire vectors, right? So you can imagine the verifier just does group operations. That's very cheap, but the committed vectors could be much larger than that. Okay, so if you want to prove that you know many openings here, okay, imagine now we have T commitments to vectors, okay, and prover knows all those openings vectors, right? And you can do exactly the same type of proof as before, just operating vectors instead of field elements where you have multiple elements, okay? And it's really cool because now the size is sort of like the complexity of the verifier is even smaller compared to, what the instance and the witness is. Okay, so what is the instance size? Well, we have T commitments, right? What is the proof size? Well, we have this field, the group element A and the field element X, and then Z, and then the vector F, which is n elements, right? So jointly, the instance and the proof size is something like T itself, right, is actually much bigger than that. It's T times n, right, because you have T commitments to vectors of length n. So what you see here now is that everything is smaller than the witness, right? From the verifier's perspective, you're seeing a smaller instance and a smaller communication of the proof, and you're actually doing less verification work. But after having gone through this Sigma protocol, the verifier knows that the prover knows all of that witness, okay? So here you actually have sublinear verification complexity. The verifier does less communication, less computation, but is still convinced that the prover knows a lot of stuff. The prover knows this huge witness of size T times n. Okay? So if T is approximately the same as n, right, then you can prove knowledge of n field elements using only square root n communication. Okay, and if you use a Fiat-Shamir heuristic, then you can make this non-interactive, right? So now we have an example of a zero-knowledge snark because it's actually a succinct proof. It's smaller than what the witness we're proving something about. And the computation is also smaller. It's also of order square root n exponentiations, even though the witness is much bigger. So it's easier to compute if you have the proof than if you had the full witness. Okay, so that's all like hints that we can do very efficient proofs of knowledge, okay? Now you can actually generalize that and also prove arithmetic circuit satisfiability, right? So what I showed you first was essentially you can prove arithmetic communication complexity of square root n. Okay, and this is tricky when you do arithmetic circuit satisfiability, right? So you can sort of commit to all the values in the wires using these generalized Peterson commitments. That's great, but it's pretty tricky to prove then that all the additions are satisfied or all the multiplication are satisfied because they may cross all sorts of places in the commitments. But it can be done, and it gives you square root in complexity. And then more recently, together with a bunch of my students and postdocs, we found a way to get logarithmic complexity. And there, the idea is that you use an n-wide generalized commitment to commit all wire values, but you never show the openings, right? Because that would be n field elements, and that would, destroy the communication complexity. Instead, you just recursively prove that those openings exist, and you sort of keep narrowing things down a logarithmic number of steps until you can use some less wide commitments to prove things. And that recursive construction actually gave us logarithmic communication complexity. Okay, so you can prove arithmetic circuit satisfiability for a circuit that has size n gates, okay? But the communication complexity in the Sigma protocol, or now it's a generalized multi-round Sigma protocol, would be logarithmic in that log n elements. Okay, so bulletproofs was an implementation of ideas building on this work that gives you logarithmic communication complexity, right? And then with a Fiat-Shamir heuristic, it becomes non-interactive, right? So now you have these snarks, right, which have the logarithmic size in the circuit that you're trying to prove. Okay.
I have a question.
Yeah.
So these constructions are really very beautiful, and they heavily rely on the homomorphic property of these commitment schemes, right?
Yeah.
So I think we have some commitment schemes which are, I'm not sure. Do we have commitment schemes which are homomorphic and they are, let's say, based on learning with rounding problem or any other problem which is secure quantum computers?
Yeah.
Do we have?
Yeah, so the pattern is very much the same, and you can use many of the same techniques. So for instance, lattice-based commitments, you have the same sort of homomorphic properties. You do have some problems, and one of the problem in lattice-based commitments is that it's not so like the clean structure. You have the group elements where you just have some randomness. Instead, you add noise typically, right? And the problem is you can have things that look like a commitment, but maybe they're not a commitment because you don't know how much noise is in it. So that's sort of like typically the problem you run into, and you sort of navigate, but people do navigate and they construct zero-knowledge proof using the same kind of principles and the same properties.
Yeah.
You can also construct homomorphic commitments from hash functions, and that's maybe a little surprising, but you can actually commit with hash functions, and then you can sort of like you can prove that you're opening things correctly, and you can actually have some homomorphic properties of those proofs. So we do have several examples of post-quantum secure things that rely on the same principles.
And the second consideration that you said, it doesn't need a homomorphism from the hash function, right?
Exactly. It's you can use SHA-256 or something like that, and you can construct a commitment scheme where you can open things homomorphically. You need to do a couple of rounds,
Okay.
but you can sort of like prove that here's an homomorphic opening of what I committed to.
Okay. So Robin also has a concept called value hiding. I don't know if you have seen it or not. Rabin and some other researchers. So they also somehow present this circuit satisfiability, but using hash functions or one-way functions or any commitment which doesn't need to be homomorphic.
Right. But are you talking about an older paper or more recent?
No, they are quite old. I think they are for 2004 or something like that.
Yeah.
But,
okay.
Yeah.
So there are many different constructions of zero knowledge proofs, right? So there's completely different constructions that rely on encryption schemes with special properties and sort of like cleverer tricks to prove that Boolean gates are satisfied. So I'm not sure that I remember the particular reference you give there, but there's certainly many constructions where you get.
Let me ask another question. So if one wants to design a protocol for post-quantum, so what are the good directions to work for this circuit satisfiability? So in which aspects should we try to improve?
Yeah, okay. Yeah, that's a good question. So by far now the bottleneck is the prover. So we have post-quantum secure zero knowledge proofs, which are public coins, so you can make them non-interactive with the Fiat-Shamir heuristic. The communication complexity can be very low, so logarithmic. Verification can be very simple as well. I mean, verification always has to read the whole instance, right? But other than that, you basically again pay nothing. And the cost is in the prover. Theoretically speaking, the prover cost can also be low, so we know that it can be just a constant times the size of the field. And that's not a constant number of exponentiations, something like that. That's really a constant number of field operations, right? So it really is comparable to just having the witness and verifying the statement yourself. It's a large constant though, right? And people are now working on sort of like, well, can we reduce that constant, or can we do other tricks and maybe accept a logarithmic overhead, but get something much better? So it's really the prover that's the bottleneck nowadays, and everything else we have reduced very significantly.
Okay, thank you very much.
Sure. Okay, so let me just wrap up here. okay, you could ask the question, can it be even smaller than logarithmic, right? And the answer to that is yes, you can do something called pairing-based SNARKs, where you can get as low as 3 group elements to prove something, okay? So non-interactive proofs that have just worked with 3 group elements, regardless of the size, okay? And it uses pairings, so now you need to have multiple groups, and you need to have this bilinear map that maps from 2 source groups into the target group and has this bilinear property. Okay, and I'll very briefly show what it looks like, but not expect you to sort of like get all the details. Looks something like this. Okay, so we have this complicated common reference string, and here it's not a random string or just a group elements, right? It's really a structured reference string that has some particular structure to these group elements. And then the prover does some computation involving a lot of sophisticated polynomials. And the verifier just needs to do a few pairings of these 3 group elements in the proof to verify. Okay, so it's a complicated construction. But what is the key message here, right, is that you can prove any really large, complicated computation with just 3 group elements, right? And I used to joke, right? So Twitter allows, I think, 144 characters, right? So we are almost in a situation where you could actually say you could take a really large and complex statement, and you could prove it with a tweet. So that's sort of like state of the art in efficiency for SNARKs. And with that, I will conclude. Thank you. And if there are any more questions, I'm happy to take them.
Okay, thank you very much, Jens, for your really nice presentation, a very nice talk, and beautiful results. From the audience, is there any questions? So if anybody has question, he can or she can raise his or her hand. We have about 1 or 2 minutes more left. So there is a question here. Would you please explain the witness indistinguishability in the discrete logarithm sigma protocol? Between which parameters the attacker has to distinguish. So I think, or her question is about if the discrete logarithm zero knowledge proof of knowledge is witness indistinguishable.
Yes. Explain, because it sort of like goes to an example of what witness indistinguishability does and does not do for you, right? So witness indistinguishability says that if I have different possible witnesses, then I cannot distinguish. Okay. Now, for the proof of knowledge of discrete logarithm, you have just one group element U, and the claim is I know that discrete logarithm. So the witness is unique. There are no other discrete logarithms. There's just the discrete logarithm, right? And that makes witness indistinguishability trivial, right? Because what does witness indistinguishability says, if I have 2 different witnesses, then I cannot distinguish. But if there's one witness, then there's nothing to distinguish from, and it's sort of like automatically satisfied. Yeah. So the answer is, first of all, the sigma protocol is witness indistinguishable because it's their knowledge. But another answer is that you could even imagine just saying, the prover saying, here's a discrete logarithm, I'll send it to you in the clear. And it's a witness indistinguishable proof, right? Because there are no other witnesses.
Yeah.
So it sort of like shows witness indistinguishability does not necessarily hide the witness, right? It only makes sure that you cannot tell which of many possible witnesses.
It's like having a crypto system whose message space is only one element, so it is secure.
Exactly, that's a good analogy. Yeah.
Okay, thank you. So let's thank Jens. Thank you very much for your talk, and hope to see you in another occasion.
Just we had one more question, Sharon. Maybe you missed it. Should I ask
sorry?
it? Or?
Yeah. Maybe I have missed it. You can.
Okay, just yes. There is a question that what would be the simulation trapdoor in this presentation examples that you had?
Yeah, okay. So that's a good question. And I think I cheated a little because typically when I talk about simulation trapdoor, we talk about, you know something secret about the setup. And here it was actually a different power we used, right? We used the power that we can rearrange the order in which we do things. So in some sense, the simulation trapdoor was, I can look into the future and see this is going to be the very fast challenge. And then I can construct the proof around that. Does that make sense?
For me, at least, yes. I hope for the question, yes. Thank you very much.
Okay. So let's thank Jens again and have a nice afternoon, everybody. I think maybe we will see you in for the next talk in half an hour. Goodbye.
Okay, all right.